Okay, in this lesson we're going to be talking about direct variation. By the end of this lesson you should be able to write and graph direct variation equations and solve real-world problems with them. Things that vary directly, these are proportional relationships. So if you recall, proportional relationships are kind of like analogies. There is this direct relationship that occurs with direct variation and with proportional relationships, such as the higher the water pressure, the faster the pool fills up. There's a direct relationship between the water pressure and the speed at which the pool fills. The faster you drive, the faster you get there. Again, there's a direct relationship between how fast you drive and how fast you get someplace. So these are things that are directly related to one another. Again, they're proportional, so they're going to be similar to those analogies that we looked at in the prior video. Along with direct variation, we have these things called joint variation, things that vary jointly. Things that vary jointly, this is when you have 2 to 3 things that are directly relating to each other. So when we look at distance, rate, and time, distance is dependent on both the rate and so the speed at which you're driving and how long you are driving. When we talk about the area is dependent, it depends, it's directly related to the size of the base and the length of the height. When we talk about interest, this little triangle down at the bottom, is related to both the principal amount that you put in, the interest rate at which it's taken, and how long you're keeping it in there. So all of these things are directly affecting the amount of interest that you earn. So when we talk about joint variation, this is when multiple things, more than 2, so 3 to 4, 3 and on, we'll leave it at that, are directly affecting each other. So we're talking about direct variation. This is a relationship between 2 variables. As one gets larger, the other one is getting proportionally larger or smaller. It's very important to note that this is a proportional relationship. So yes, it's increasing or it's decreasing, but it's increasing or decreasing proportionally. K, which you'll notice in our equation of y equals kx, is in the same spot as slope. They do represent the same thing, but K is a little bit special in how you can find it. We don't have to go through as much work as we do for just regular old slope. When we talk about the graph for direct variation, the graph for direct variation is always linear. It's always going to pass through the origin, meaning it's proportional, and the slope is going to be the K. So when we're talking about the slope of our graph, it's the K in our direct variation equation. So you can find it the same way that you find slope. When we're checking for direct variation, if we're checking from ordered pairs, we're checking to see if those ratios, okay, of y to x within each point is proportional. So they should be equal. Their cross product should be equal. We talked about that in the last video. Is the graph a line that goes through the origin? Is the graph a line that goes through 0, 0? So if you're checking from the graph, it should be going through the origin. And if you're writing the equation, if you're attempting to write the equation, can the equation be written as y equals kx? Meaning there is no y-intercept shown. That y-intercept would be 0. Okay? So when it's 0, we don't write it. So if there's a number there, if it's kx plus a number, then we know that it's not proportional, which means it's not direct variation. We talked about joint variation. Joint variation is when a quantity depends on the product of 2 or more other quantities. It depends on them together. So we talked about distance, rate, and time. Distance depends on both the rate and the time. So this idea of joint variation, it's not just dependent on one item, but now it's dependent on at least 2 other quantities. All right, we're going to look at a couple of equations. We're going to determine if these equations are written in direct variation. Remember that when we're writing direct variation, it is y equals kx. So if the equation's not already in that form, we need to manipulate it. We need to solve it so that it is in that form. So here, this would mean adding x to both sides so that y is by itself. So we would have y equals x plus 1. This is not in kx form because we have a y-intercept of 1. So this does not have direct variation. If we look at the second one, this would require me doing two things. First, subtracting off the 4x, because we take care of adding and subtracting first. We want to get the y by itself. So we have negative 5y is equal to negative 4x plus 0, but I don't have to write 0 this time. And then we're going to divide by the 5, because we want to get rid of this negative 5. We don't want negative 5y, we just want y. So as I divide by negative 5, we end up with a fraction of 4 over 5, positive 4 over 5, because the negatives will cancel out, x. And this does have direct variation because we're in that kx form. K, or constant of proportionality, is for fifths. When we talk about writing direct variation equation as it relates to y and x, okay, remember that our equation that we're writing is y equals kx. So if we don't know k, we do know y and we do know x, so we can substitute in those values. So in this particular equation in A, we know that y is 8. We're trying to find k. We know x is 4. And so I can solve it. We're solving for k, so I need to get rid of this 4. We would get rid of the 4 by dividing both sides by 4. And so we know that k is equal to 2. So my direct variation equation, y equals kx, remember I don't need the y and the x to have values in it necessarily, now that I know k. So my equation here would be y equals 2x. We want the y equals 2x equation because then we can use that equation to find any value. So for this particular problem, it wants us to figure out y when x is 5. So in my direct variation equation of y equals 2x, we're looking for y when x is 5. So instead of x, we put 5. And the y value would be 10. Okay, let's try it again. So we have y equals 1 1/4 when x is equal to 5. The one thing I would do here is I would change this 1 1/4 to an improper fraction, which would be 5 over 4. It's going to be a little bit easier to deal with when we want to multiply. So here, again, our y is 5 over 4. We're looking for k equals k times 5. I would divide both sides by 5. However, because I have a fraction here, it's going to be a little bit easier to go ahead and multiply by the reciprocal. The reciprocal is the same thing as dividing. So if I multiply both sides by 1/5, which would be the reciprocal of 5, that would be the same thing as dividing by 5. It just works out a little bit better here because of this fraction, because it's going to be a little bit harder to divide 5 over 4 by 5. So if we multiply by the reciprocal, the 5 and the 1/5 cancel each other out. 5 times 1 is 5. And actually the 5 in the bottom and the 5 in the top, they can undo each other. And that leaves you with 1/4. So we have k is equal to 1/4. Again, now that we know what k is, we can go back and we can write our equation. So y equals 1/4 x. And then substitute in the 12 this time, because we want to know what y is when x is 12. We look at 1/4 of 12. 1/4 of 12 would be 3. Right. I want to write the equation for the direct variation. So for writing the equation, remember that these are linear relationships. We will find the slope by looking at the change in the y and the change in the x. Remember that when you are checking a table, you need to confirm that that point has 0, 0. The way to confirm that is by checking the ratios. So that would be by doing the y over x for each one. In this case, this table is proportional. So if we're writing the equation here, we would just need to look at one of these points. But let's check it. So we have y over x is 2.5 over 2. If we did the second one, it'd be 8.75 over 7, or negative 7. And negative 6.25 over 5. When you check each one, the ratio here would be 1.25, 1.25, negative 1.25. So all of them are the same. So this will tell you that 0, 0 is in the table, that this is a proportional table. You want to check the ratios of y over x for all the points that are in there. And once you've done that, the nice thing about this is that now you know k. K is that ratio of y over x. And so our equation here would be y equals 1.25 x, because we've already found our constant of proportionality here. For looking at our graph, we know that it's proportional. It goes through the origin. So all I need to find is k. Or actually, let's look at what we were doing before. This y equals kx. We can find k. We have a point. 6 is the y value. 4 is the x value. And then solve for it, right? So the 4's we cancel out here. K is equal to 6 over 4 or 3 over 2. And then we could write the equation as y equals 3 halves x. For looking at direct variation from the equation, we have a competitive race walkers move at a speed of about 9 miles per hour. These problems are pretty simple. Y equals 9x. This the distance is equal to 9 miles per hour. So you're just writing the rate. The 9 per hour is the rate. When we look at Michaela charges 8 hours or $8 per hour. Again, this would just be y equals 8x. The per hour part would be the direct variation equation. Looking at the next couple of examples, we're looking at the graph. We want to graph it. All of our direct variation relationships will start at the origin. And if you recall from our lesson on slope, the k tells us if we're going up and down and right and left. So in this case, the positive 1 tells me to go up 1. The positive 3 tells me to go to the right 3 and to continue that pattern. Or I can go backwards, so I can go down 1 and left 3. That would be the same relationship here. For looking at 4x, again, we're starting at the origin. 4 is the same thing as saying 4 over 1. So I can go up 4 and right 1, or I could go down 4 and left 1. That would be the same. Okay, so if I need to go backwards to get more points, just do the opposite. Okay, we have negative 1/2 x. Again, we're going to start at the origin. This time we're going to go down 1 and right 2, or I could go up 1 and to the left. So kind of keep that in mind, that there are 2 directions that you can go. You're just doing the opposite to get the other direction. But all of these graphs will start at the origin, and then they will move according to the constant of variation. For looking at joint variation, again, you're writing the equation. So it says, suppose R varies jointly as P and Q. So this says that R is dependent on the relationship of P and Q. So that R is 24. So if R is 24 and P is 3, and remember, let me change this equation right here. So R is dependent. So K is our constant of variation. This is our slope. P and Q, remember that K is always going to be here. We still need to figure out what K is even in this equation. So R is 24, P is 3, Q is 2. So we would set up this equation so that we solve for K. So we have 24 is equal to K times 6. If we divide both sides by 6, we get that K is 4. So this particular equation would be R equals 4, now that we know what K is, times P times Q. And then we could figure out what R is when P is 2 and R is 3. So if P is 2 and Q is 3, R would be the product of those 3 things, so that would be 24. So R would be 24. So same thing as what we had over here. Right. We know that a relationship has direct variation when. So how do we determine if a relationship has direct variation? This is what I would like for you to consider before watching the next video.